Spector. Vero already said who I am and what I do. So I'm an organic chemist, but I do a lot of work on aesthetics in chemistry, and I don't mean like the aesthetics of doing chemistry, but the aesthetics of the representations that chemists use. So you'll see that as I go along. And this particular talk is on what I call the molecular elusive. It's really on time and aesthetics in chemistry, which is a pretty complicated subject. So I'm just going to give you, I hope, somewhat of an introduction to what that means. So how many of you are scientists? So some of you probably know about time in chemistry in various ways. Okay. So if you're thinking about chemical reactions can occur over lots and lots of different time scales. So we can have really, really slow reactions. This is just a pretty famous piece by Chris Burden, famous artist. Usually he's known as a performance artist, but this is all these pieces of metal that were dropped down into this concrete slab, and then they rusted. So the reaction that I'm referring to here is rusting, which is a chemical process that we usually think of as being a pretty slow chemical process. And then we can have really fast chemical processes like explosions would be a good example of a very fast chemical process. The reaction starts and really quick. And then we can have reactions that are, let's see if I can get this thing to work. How do I make this go? There it is. I don't know how many of you have seen this. It's called the oscillating clock reaction. You might have seen it in your general chemistry class if you ever took that. And it's a reaction that you can watch the reactions actually occurring on a, as I say, a perceptible time scale. So you'll see in a second, it just keeps switching color from one thing to the next to the next. So it's an oscillating reaction. It's a very cool reaction. My students are always mostly fascinated by the stir plate on the
What's the chemical reaction?
Oh, yeah.
It's some kind of iodine reaction, but I don't know the exact process going on in the reaction. Sorry. But we can look it up after. There's not many of these oscillating clock reactions. There's just a few chemical systems that do this. They're not an organic chemist. This is some kind of inorganic chemistry. All right. So generally, when you think about reactions, and most people think about reactions if they think about them at all, or chemical processes, you usually think about, let's say, rusting. You have iron, and then in the end you have rust. So there's some process that goes from some starting material, the iron, to the end thing, which is rust. And unless you're a chemist, you probably don't think about it, but in this process, along the path from whatever the starting material is to whatever the product is, there's a whole bunch of very short-lived species that occur along the path, transient, very short-lived molecular species. So for this particular thing, this is just sort of cartoon of what happens when things rust. But in this process, you get oxidation of iron to an iron plus 2 species, and then oxidation of that to an iron plus 3 species, and then it combines with oxygen, then it forms iron oxide, and it then gets hydrated with water. So all these things are happening when you rust, right? So all these intermediary steps in this process, but although the reaction is very slow in sort of the real-time world, right? I mean, something rusts, it might take years for something to rust. The actual processes in between are incredibly, incredibly fast. So this is really what I'm interested in. I'm not really interested in the real-time aspects of the science, of going from starting material to product, whether fast or slow. I'm interested in the intermediate things that exist for incredibly short amounts of time. So one thing that is kind of interesting about this, we think about it as being fast or slow, something going quickly or going slowly. But actually, the rates of reactions in the end is based actually more on how often a reaction occurs on a molecular scale, not how quickly it occurs on a molecular scale, because all reactions on the molecular scale are actually really, really fast once you have enough energy in there to make them go. Okay, so the main thing I want to point out on here, whether you got all that or not, is that there's two kind of main species that chemists concern themselves with in between starting material and product. So you don't even need to know what all these things mean, and you don't need to at all, only my students do. Okay, so you go from here to here. This would be starting material product. But in between, there's these things we call transition states at the top of this hill. And then we also have something called intermediates. So again, for those of you who studied chemistry, I'm sure you've seen these things before, right? So this is the highest energy point. When we start a reaction doesn't just go from here to here downhill like this, like starting material to some product. If we draw it on an energy diagram, this is called a potential energy diagram. It has to go over an activation energy barrier, which goes uphill, and then sometimes we get a little dip, and then it goes downhill like this. So there's these species that get generated all the way along the path until we go from starting material to product. Yeah?
So that means you have to supply some energy first.
You
in
do.
order to get it
So
started.
sometimes there's enough energy in the room, because the energy is heat, usually, right? So there's enough energy at 25 degrees C, which is usual room temperature, to allow a reaction. Sometimes you have to heat it up. Sometimes you have to add light. There's all different ways to do reactions. But yes, you have to add energy in to do a reaction in some way. So no reaction would occur at absolute zero, basically. So we have these two things, transition states and intermediates. And this is something that I wanted you to notice down here, is that the transition states exist for femtoseconds. So 10 to the minus 15 seconds. That's how long those species exist. Very short time period. Intermediates are slightly longer lived species. They're the things that exist in the little dip there. They exist on the 10 to the minus 10 or 10 to the minus 6 time scale. Seconds time scale.
What's the horizontal axis?
This horizontal axis here is just the we call it the reaction coordinate. So are you asking what this SM1 means? Or are you asking what the axis is?
What is the axis?
The axis is just the way the reaction proceeds. So it goes from starting material to product. So it's just reactants, products.
So it's not time.
It translates into time, actually. That's a great question. So even though time isn't explicitly on here, time is implied by this diagram, that we start with something, some time passes. It might be a really fast time or a really slow time, and then we go to products. So it's not time. But it's implied by that we're starting with something and ending with something else. Yeah?
Does these intermediate reactions have an effect on the final result?
What these things are, the transition state? Yeah, they have an effect. What they are affects what product you end up getting in the end. And every reaction has a different transition states and different intermediates. And some reactions, as shown here, only have transition states and no intermediates. Yeah?
Can you refresh my memory what the time is, say, on a flame front from one end of the reaction to the other side of the flame front? Like, is that millions of a second? Is that thousands of a second?
I don't know if I know the answer to
Okay.
the
I'm
exact
just trying to put it
answer to
into
your
perspective.
question.
Yeah.
For combustion type
Yeah, yeah, yeah.
reaction. It's
Your steady
probably, I would say, something like nanoseconds, maybe, would be my guess. Yeah. Okay, so what does this have to do with aesthetics? You're probably still wondering. Like I said, something about aesthetics early on. Okay, so generally, people who study molecular aesthetics or chemical aesthetics, which is like me and a few, like 5 other people in the world, I guess. So when we do this, most of the work that's been done has been done on stable or very low energy ground state things that hang out in the world for a long time, as shown here. So this is a buckyball. You guys have probably seen this structure in, like, I don't know, various places, commercials or something like that, right? So this is a chemical structure, and it's a very long-lived, stable thing. And there's been lots of sort of structuralist aesthetics applied to these kinds of systems. So things like symmetry, but also other things. But very little attention has been paid attention to these very short time scale species, and that's what I'm really interested in at this point. So just to give you a feel for it, chemists love these really short time scale species. Even though we can't really capture them, or we can capture them in very clever ways, as I'll show you, but we just love them. So this is a quote from Polanyi and Zual. Zual won the Nobel Prize for work related to femtospectroscopy, as I'll talk about. And he says this about the transition state. That's the high energy point on the diagram. The transition state is neither one thing, namely chemical reagents, nor the other, reaction products. Instead, it illustrates the mystical events of transubstantiation. That's really strong language for a scientist. Okay. Here's another quote for another Nobel Prize chemist, okay, Donald Cram. And he's writing about this molecule, this one right here. It's just a square. It looks like a square with some lines in it for a non-chemist, right? And he says this, and it's called this, cyclobutadiene. That's the name of the molecule. Cyclobutadiene is the Mona Lisa of organic chemistry in its ability to elicit wonder, stimulate the imagination, and challenge interpretive instincts. No other organic compound combines such a fleeting existence and so many different syntheses, etc. So we talk about it in these incredibly emotional ways, really, aesthetic ways. Even though they exist for a 15th of a second or a 10th of a second, we have all this love for these kinds of things.
Are you saying cyclobutadiene does not exist independent of these reactions?
Right, it only exists for a moment. It's like you start with this, which is stable. You go uphill. This is related to this dip in the diagram at the high energy place. This is an energy axis here. It exists for maybe 10 to the minus 10 seconds or something like that. And then it becomes this, which is another stable thing. Is that what you're asking me?
Well, yes, you can't have pure cyclobutadiene.
No, you cannot. No. You can if you're at 4 degrees Kelvin.
Oh, okay.
Yeah, it's pretty hard to be at 4 degrees Kelvin, but that's about the only time you could actually have that and let it hang out.
So that thing on the left, is that just kind of coupled with the iron atom sitting in the middle of the ring?
Yeah,
Or how does
it
that hold
is. It's
together?
like this is a bond that is bound to the electrons here in this ring, and this is iron tricarbonyl, so it's the iron is basically chelating
So
to that
that's stable
system.
enough that the iron can actually stabilize that.
Yes, very stable.
Great.
You can put it in a bottle.
Interesting.
Yeah, absolutely.
Is the image on the right the product?
Yeah, the image on the right is the product. So we're going starting material, intermediate product. So we always go from left to right. We always read from left to right in reactions.
The CH4, does it gain or lose something that's identifiable before it becomes product?
Not quite getting your question. Try again.
I'm trying to I'm trying to pick up what changes from intermediate to product.
Oh.
No.
Okay, so the product, you see, this is the cyclobutadiene. It's attached to an iron that he was asking about. That stabilizes that, okay? And then it gets released. We add this cerium, that cerium ion in. It releases it. It makes this. This then reacts with another of this to make this.
And that's pure carbon and hydrogen.
Pure
nothing
carbon.
else.
I guess I should say that. I make too many assumptions. This is carbon, 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 with H's hanging off
So
at each one of the
whatever
carbons.
the iron is gone and the O is gone, everything goes
Everything's
away.
gone away. It's a side product, but we don't care because I'm an organic chemist, so I don't care about inorganic things. Okay. All right. So another thing that I would say, and this is actually when Zual won his Nobel Prize, and they always have these press releases, if you ever look at the Nobel Prize sites, about things, and somebody writes up about what the person's work is about. And they wrote that femtochemistry, which is the chemistry of these very short-lived species, has changed our view of chemical reactions. The most important part here for me says we can now see the movement of individual atoms, and we imagine them. They are no longer invisible. So that's quite a statement to say, since we can't actually see atoms at all. But that's what they're writing on the Nobel Prize page. So what does that really mean? What that means is that we can illustrate molecules, just like you guys were asking me, like, what is this thing, this drawing that you're showing, what is that? That's an illustration, a representation that a person draws of a molecule that we actually can't see, but that what we imagine in some way is representative of its properties. That's really what those representations are. So there's a quote from a philosopher, Joachim Schumer. You can see he does this stuff on aesthetics of chemistry too. It's the molecules, and what he means there is the representations of molecules, and only the molecules for which claims of beauty and artistic creativity are justified, no matter what sensual qualities the corresponding materials have. Okay, so he's saying it's these representations that are the things that are actually aesthetic to a chemist. And that for sure is true. So let me give you a little bit more feeling about this.
One more question. If
Yeah.
you go back, that picture in the background has 8 carbon atoms and 8 hydrogen.
Yes.
So that seems to have the same number as your final product.
Of the other thing.
Is that actually
That's
the-
true. It's an isomer of it. It is true. It is. This is cubane. I don't know if you can see. It's
Yeah,
a
sure.
cube-shaped molecule.
But
That's right.
If the other one was supposed to represent a cube, then it was a very poor representation.
Well, it's not.
because
It's a different molecule. It's an isomer
Oh,
of
really?
it. It's not the
Oh,
same
okay.
molecule,
Not the
but
same.
but they have the same
Same.
carbon and hydrogen count,
Mhm.
and you could make one sort of from the other.
Yeah, and both of them are stable.
Yes, both of them are stable. That is true. Okay, so let me just talk a little bit about what we really mean when we say we see a transition state and why he won the Nobel Prize. So Wall won the Nobel Prize for this. This is an example from one of his papers. Okay, so what does this mean? What they actually do is they use this very fast laser. And with the very fast laser, they can trace in time a resonance. Okay, so they're looking at the molecule, and they're looking at the molecule absorbing the laser light, and when it absorbs at a certain point, they see a blip. Okay, so that's what they get. That's the data. And then what they do is they trace that data into a potential energy diagram. This is a 3-dimensional one rather than the 2-dimensional ones that I was showing you. Okay, so they take it and they translate it onto this. And then they put pictures next to places along this potential energy diagram that says, this is starting material, okay, actually this is starting material, this is product, and this is the transition state, okay? So that's what they mean by seeing the transition state, or seeing molecules making and breaking. They're doing it for this particular reaction, going from this stuff, doesn't really matter what it is, to this stuff. The main thing you can see is like you've got these 2 things on the same side and these 2 things on the opposite side over
But
here.
if that graph is the only data they have, they're just guessing at the rest of this.
Well, we can know what the starting material looks like through other means, and we can know what the product looks like through other means, other types of spectroscopy where we can show where the atoms are. We can use X-rays and stuff to figure out where the atoms are in some relation, and it's a fair mapping. But the other one in between is just, in a way, a speculation. Yeah. Yes.
In the energy diagram, I assume vertically is energy. Energy. What are the other 2 axes? Why are there 2 other axes? Is one time or what?
So, you guys are asking such deep questions about these. It's amazing. Now, what it is what's called the dihedral angle, which is, imagine going from this to this.
Okay.
You have an angle where you're twisting, and it's the angle between this, 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 and this. So 2 planes turning. That's the angles being shown here. Okay? Is that what
That's
you're asking?
one parameter. What about the other parameter?
And the other parameter is energy here.
Yes.
So it's 2 dihedrals and a...
Oh, they're plotted separately.
Yeah.
Okay.
Yeah.
So in theory, you only have 2 minutes left, but because
Okay,
you
but
made
I'm
questions,
gonna interrupt.
go.
Okay, let me keep going. Yeah, so this is all what I was saying. You have the time snapshot, the potential energy surface, and then they say, aha, this is the transition state. Okay. And this gets to one of the earlier questions, which was, where's the time on the axis? Somebody asked me about time. And it says here, this is another philosopher of science, Stephen Weinberg, quite well-known philosopher of science, who says transition state theory, which is what this is all about, allows chemists, in a sense, to visualize time itself, time that is completely tethered to space. So, because we have things going from starting material to product, right? We essentially implicitly have time on these diagrams, and so it allows us to understand time. We also know explicitly that transition states exist for a femtosecond. So we know that information. Okay, so what's the aesthetic thing? I just have a few more slides and then we'll stop. Okay, so I can't get into all the aesthetics of it. It's pretty complex because you have to go into the aesthetics of time, which is a really, really complicated thing. But one thing is, when you think about these static structures of a transition state or an intermediate, basically they're compressing all this information into a very simple looking structure. So here's cyclobutadiene. It just looks like a square, like a modrion or something, right? And then we have, it has information about time in it. We know it exists for like 10 to the minus 10 seconds, right? We have space because we're drawing something spatially, right? And we know that it's a high energy species. So all of that information just in that static picture for a chemist is in that one little picture of that square for a chemist. Okay. The other thing in terms of time is that, of course, there's a narrative going on when you look at a diagram like I've been showing you guys, going from starting material to product through some intermediate or transition state. There's a narrative aspect to it. So this is, again, another philosopher says that, it's a philosopher of art or photography, talking about that static pictures implicitly have a narrative function, right? So if we look at this famous photograph by Edgerton, right, we can have this static picture, but you guys can all imagine that shooting of the gun, the bullet coming out of the gun, going through the apple, coming out the other side. So even though this is a static picture, there's a narrative implicit in this picture that we can all easily imagine. And that's true for potential energy diagrams for chemists too, right? We know starting material, we know the product, and we can imagine the path, even if we just have the intermediate thing, that little slice of action, we can imagine what it is. Okay. Let me go here. This is a long quote, so I won't read through all of it for you. But just to say that, let's say this, that we can't ever know the infinite, right? We can't know the infinitesimal, right? We can't know anything but a little slice of time. We can't know the second as it's passing. You guys get what I'm saying, right? That's basically what this is saying. So this particular philosopher says that we can't know this instant that's happening, but we can know a little time slice, a very, very short time slice of something happening. And he calls it a specious instant. Okay? So you can read through that yourself because it will take me too long. And this is my last thing. So basically, instants have no duration and therefore are imperceptible. Specious instants are the smallest perceivable part of an instant. So that should make sense to you. Time frames of transition states and intermediates are therefore specious instants because they're extremely, extremely short, but we can know them. And therefore, and this is a big part of the aesthetics of these species, depictions of transition states and intermediates express the imperceptibility of time. So that's my conclusion for